Today's lesson, concurrent lines, medians, and altitudes. When three or more lines intersect in exactly one point, they are called concurrent lines. The point at which they intersect is called the point of concurrency. For any triangle, 4 different sets of lines are concurrent. We're going to look at least a couple of those today. So if you have just 3 lines intersecting all in the same place, that point where they all intersect is called the point of concurrency, and the lines are said to be concurrent.
How does it say for 3 or more lines? And it says 4 different types of lines?
There are 4 different types of things being types of lines. Like medians is one type of lines that we could see in a triangle. Perpendicular bisectors of sides is another type of lines we could see in a triangle. Okay? There's 4 different sets of those kinds of lines that turn out to be concurrent. And we're going to try to study at least 2 of those today. So here we go. We got a couple of theorems. The first one says the perpendicular bisectors of the sides of a triangle are concurrent at a point equidistant from the vertices. So looking at this diagram, which things are we talking about? The blue lines segments or the black line segments? The perpendicular bisectors of the sides. Is that the black or the blue? It's the black. What are the blues? What do the blues appear to be? They might be angle bisectors. I'm not sure it is at Q and S, but they might be intended to be that, and it's just not a great diagram. So, but that first theorem is referring to these black lines. They're perpendicular to the sides, and they're also cutting the sides in half. That makes them perpendicular bisectors, right? So if we were looking at the whole lines, we'd see these big 3 lines running through here. Well, we don't want to look at that. It kind of dirties up the diagram. We just want to look at these segments. If we take a triangle and draw those lines, it doesn't matter what kind of triangle that is. This is an acute scalene-looking triangle, right? It could be an obtuse scalene or an obtuse isosceles or whatever. It's still going to turn out that those sides, those lines are going to be concurrent at some point. And that point's going to be equidistant from the vertices. What does that mean, the fact that it's equidistant? There we go. What does the fact that it's equidistant from the vertices mean? This point is, what does it mean to be equidistant? It's the same distance from Q as it is from S as it is from R, right? That point in the middle, let's call it C, is the same distance from all of those. This next theorem doesn't really have a good diagram because these blue lines are just showing that equal distance from that point. So that we're not going to see that picture there, but it says the bisectors of the angles of a triangle are congruent at a point equidistant from the sides. So if we take the actual angle bisectors and we draw all those are going to be congruent at some point, concurrent at some point that's equidistant from the sides. So that can't be at point C, can it? Because point C is not equidistant from the sides. It's a lot closer to side SQ than it is to side QR, right? So those are going to be somewhere different. It also turns out that the point of concurrency of the perpendicular bisectors of a triangle is called the circumcenter of the triangle. So this point C is the center of that blue circle. It's also called the circumcenter of the triangle. Have you guys talked about the difference between circumscribed and inscribed yet? We say that this circle is circumscribed about the triangle. That's why this point is the circumcenter. Circumscribed circle, circumcenter. It goes around the outside of it. If we drew the circle inside the triangle, it would be an inscribed circle. It's inscribed. Scribed means drawn, right? Circum means about. So about drawn or drawn about. That's what circumscribed means. Inscribed would mean indrawn or drawn inside. So that's where that's working. Let me use some of this. Maybe we'll get a better handle on it. This is a key slide right here. Find the center of the circle that you can circumscribe about the triangle with these 3 vertices, 0, 0, negative 8, 0, and 0, negative, or 0, 6. So we've got these 3 points. We're going to plot them. Those 3 points are going to be the vertices of a triangle. We're going to try to find the center of the circle that would be drawn perfectly through those vertices. Okay? So we're going to have to find that circumcenter of the triangle. So let's go ahead and plot the points. 0, 0 is a pretty straightforward plot right at the origin. So we'll put 0, 0 down. Negative 8, 0, left 8 and up 0. That's a pretty straightforward plot. And then finally 0, 6 is going to be up here. And then those 3 vertices are supposed to be the 3 sides of a triangle. So let's go ahead and sketch the triangle in. Let's got a triangle in here. How are we going to find the center point of where the circle goes so that I can draw a circle perfectly through all these points and have it be a nice round circle? Say that again? I could try a protractor and guess and check a little bit, but there's actually an easier way. We can use that first theorem from the other page and that little statement that was at the end. It said that say that again? I'm not ready to draw a circle because I don't know where the center is yet. Let's go back up to right here. The point of concurrency of the perpendicular bisectors of a triangle is called the circumcenter of the circle. That's also the center of the circle, right? This point C is the center of the circle. It's the point of concurrency of the perpendicular bisectors. So if I have these 3 points on the other slide, Q, R, and S type points, how can I find this center point C? Where's that center point going to be? Where what all meets? The perpendicular bisectors. And based on the diagram that I had on the other slide, is it pretty easy to find at least a couple of those perpendicular bisectors? Yeah, because they're vertical and horizontal sides of a triangle. So let's go back to that. Put those points back down. Put the triangle back down. Can I find the midpoint between the point 0, 0 and the point negative 8, 0? It's going to be at negative 4, 0, right? And if I just draw a vertical line, is that going to be perpendicular to the segment that's down here? This horizontal segment? Sure. So let's go ahead and sketch that segment in. Can I find a perpendicular bisector between 0, 0 and 0, 6? Where's the midpoint going to be? At 3. And I just need to draw a horizontal line, right? And it turns out that in this right triangle, those 2 segments intersect right on the hypotenuse. What point on the hypotenuse did they happen to intersect at? The midpoint, right? Because the perpendicular bisector coming through there is going to go perpendicular to the hypotenuse and right through that midpoint. So that circumcenter might be inside the triangle, like on the previous slide, might be on the triangle, like on this slide, or there could be a case we could find where it's outside the triangle. So that's the center point I need to use. Where's that center point? Negative 4, up 3, right? I can go ahead and put my compass there. If I was doing this by hand, I'd put a compass there. And then how would I figure out the radius to draw? Yeah, would it matter which dot I use? No, because it says it's supposed to be equidistant from all these, right? So it doesn't matter which dot I use. I just use one of those distances for a radius, and I can draw that circle right through all the points. So the answer to the question is really, all I wanted to know is the center, right? Find the center of the circle. Well, the center is going to be at negative 4, 3. Pretty easy when we've got nice vertical and horizontal segments of a circle to work with. Questions so far? So theoretically, we could hand out a piece of paper to every person. They could put 3 dots on it. You could hand it to a different person. They could connect the 3 dots into a triangle and find a pretty good estimate of where the center would be to draw a circle through all 3 points, right? You could do that with a couple rulers and a compass. The compass to help you draw the circle. Yeah.